Hello. This video is going to be on air resistance. A good place to start for air resistance, I think, is analyzing a ball moving through the air. Say this ball was just thrown up, so it has some velocity moving up and to the right. This ball will be subject to some weight force down and some drag force opposite to the direction of the velocity. That is what this equation is going to represent, meaning the drag force is going to be dependent on the magnitude of the velocity. It is dependent on other things like the size and the shape and the medium that the object is traveling through. But for now, we're just going to look at the velocity of the object. The drag force can be broken up into two terms, a linear and a quadratic term. BV is our linear term. CV squared is our quadratic term. The quick remark, the linear term, it's going to be much easier to solve, which is really nice, but it is only applicable to oftentimes small things traveling through a very low viscous fluid, like the air, and the quadratic term is going to be harder to solve, but more applicable for everyday life things that we see, bigger things traveling through less viscous fluids. Kind of sucks, but that's the way it is. Anyways, this linear term, BV, I'll say F linear equal to BV, and this is such that B, this constant B, is equal to beta times D. D is going to be the diameter of the object, and beta is a number or constant that is just dependent on the medium that the object is traveling through. And then the quadratic term is going to be quite similar, CV squared. This is such that C is equal to gamma D squared, again, D being the diameter of the object, and gamma, again, being dependent on the medium that the object is traveling through. Okay. From here, I think we can start making an equation describing our object up here. This guy, we can make an equation from Newton's second law, mr double dot, mr vector double dot. That is going to be equal to the sum of the forces, so mg going down, and then minus BV. Oh, and for this video, we're only going to be looking at the linear air resistance term. So this guy here, just because it's going to be easier to solve. So it's going to be a good kind of stepping stone towards the full equation that is the linear and the quadratic. Anyways, this is going to be our equation of motion for the object if we're only considering the linear air resistance term. And this, if you notice, this term doesn't have any r's in it. It's not dependent on position. So we can write this as mv dot equal to mg minus bv. And what we want to do from here, and I think what you should always do, is break this up into its component form. So this will give us mv dot x. That's going to be equal to the forces in the x direction, which is only going to be the linear air resistance in that x direction, it is going to be in the negative x direction because it is opposite to the motion. So that will be negative bvx. And then we will have the y component, mv vector dot y. We're going to have a force of gravity downwards, mg, and then the drag downwards in the y direction minus bvy. This is nice, breaking up our equation into its components, because now we have two uncoupled equations that are easy to solve. That is going to be much easier compared to the quadratic term. In the quadratic term, I'll write it out just so we can see it. Negative c square root vx squared plus vy squared. Outside of that is vx, and then you have mvy. You have your weight force, and then same thing, x squared plus vy squared, and then vy out here. These two equations are what we call coupled, which is going to make it a lot harder to actually solve. I think we will do it later, but we're not going to be looking at the quadratic terms for now. I just want you to see why breaking it up into its components and getting these is going to be so easy, because the x term is not dependent on y, and the y term is not dependent on x, which is really, really easy to solve. Cool. If we first look at the horizontal component, so that is going to be mvx equal to negative bvx. We can go ahead and rewrite this for velocity. If we divide over that m, vx dot, that's going to be negative b over m vx. Now this negative b over m term is often written as its own variable, oftentimes k. So this would go to vx dot equal to negative k vx. And with this equation, well, maybe I'll highlight it. This equation is telling us that the first derivative, this term, is equal to the original function times some negative constant. And that only happens from exponential terms, right? If you have e to the bx and you're differentiating with respect to dx, that would give you be to the bx, right? You have your original function. The first derivative of this function gives you the original function multiplied by some constant. So, solving for v of x, it's going to be, and this is a time derivative, because we're going to be able to find position eventually. This is going to be equal to some constant times the exponential. To determine what a is going to be an initial condition, and that is going to be when t equals 0. And that is going to be at t equals 0. That's going to be our initial velocity, vx naught. So plugging that in, we have vx of t is equal to vx naught times e to the negative kt. Now, again, a little weird. The stuff in the exponential is going to go through a change of variables. We're going to add in the variable tau, which is going to be 1 over k. And remember what k was. K was negative b over m. Or k was just b over m. So 1 over k is going to be m over b. Why it's a little hard to understand, but I feel like that's most of the math for air resistance stuff. It's just a very common thing that they do. If this is your first time seeing it, I wouldn't really expect you to kind of totally get as to why they do it. It's just something that does happen. Anyways, we have an equation for velocity, and what we can do is take the integral of velocity to get position, right? Velocity is the first derivative of position. So to go from velocity to position, we integrate. So this would be, you want to integrate from time equals 0 to some other time t, some arbitrary time t. And we're integrating our velocity term with respect to dt. Oftentimes what you will see if you're integrating bounds are the same as the variable in your integrand, oftentimes they will denote the variable in the integrand with a prime to differentiate the two variables. So we have integral of 0 to t vx of t prime dt prime now. They mean it's still denoting the same thing. It's still denoting time. It's just kind of differentiating between the t and the integration bound. All right, and this is equal to the position at t minus the position at time equals 0. And then we can solve this if we just move the position at time equals 0 over to the other side. We will have an equation for the position at some time. So that's going to be x naught, or x of 0, and then plus the integral from 0 to t. And here we're going to plug in vx of t is going to be this stuff here. So we plug in vx naught, e, and then here we're going to put in that change of variables. We have negative t, this is still prime. We have negative t divided by our new variable tau, and this is with respect to dt prime. And this is going to be oftentimes at time equals 0, we're going to consider the position to be 0. That doesn't always have to be the case, but this will be 0 plus negative vx naught tau e to the negative t prime over tau from 0 to t. And this, let's see, we can get rid of that 0 if its initial position is 0. Initial position is 0 at time equals 0. Okay, and then this guy is going to be negative vx naught tau e to the negative t over tau minus negative vx naught tau e to the negative 0 over tau. And remember that anything to the 0th power is just going to be 1. So this will give us negative vx naught tau e to the negative t over tau. Minus a negative goes to plus, so this will be plus v x naught tau. This guy goes to 1, so we don't need to write anything in there. We can factor out a v x naught tau, and then we'd have v x naught tau equal to, this guy goes to 1, and then factoring out a v x naught tau of this minus e to the negative t over tau. Cool. Here we have solved the horizontal position as a function of time given our air resistance, our drag force. Now, vertical. Now we want to look at the vertical motion component. So the horizontal component, we had mvx equal to negative bvx. Now we have mvy dot equal to the gravitational force minus bvy. Okay, now in the vertical case, we have to take into account the possibility of terminal velocity. And that terminal velocity is the case when the weight force is equal to the drag force. Right? Because when that is the case, if you drop a ball from rest and it falls straight down, if the drag force equals the weight force, then the net force is equal to 0. Therefore, the acceleration is equal to 0, and therefore it moves at constant velocity. Right? And that is something we must take into account, and that happens. Let's see, when Vy equals V tur, we can find this by which one do we want? Oh, it's right here. If this is equal to 0, right? V dot, that's the acceleration. If you are in terminal velocity, the acceleration is 0, so this whole term would go to 0 if we are in terminal velocity. So if we want to find when our object is at terminal velocity, we set this equal to 0, so we'd have 0 equal to mg minus bvy, and we want to solve for the velocity in the y direction. So if we add over our negative term, mg, divide by b, that means vy is equal to mg over b. That is when we are at terminal velocity. This equal to v tur, terminal velocity. And that's specifically for linear drag. Remember, we are only in the linear drag case. So if we have mv dot equal to, this will become negative b times vy minus v tur. Right, you can check the equivalence of this. If we say, now if you have terminal velocity, this term becomes a constant, and so you can set it equal to just a variable. Now, oftentimes I've seen it set to u, so if u equals vy minus v tur, we have an equation equivalent to what we had in our horizontal case, right? So this would be negative bu, and this is saying essentially the same thing, where the first derivative is equal to a negative constant times itself. All right, this guy means that this is vy minus vter, and that's equal to a constant times itself, which only happens in the exponential case. And as we saw from the horizontal component, what we derived from up there, we'd have a e to the negative t over tau. And when t equals 0, vy is going to be vy naught. Therefore, our a initial condition is vy naught minus vter. So vy as a function of time is going to be vter plus vy naught minus vter with the e to the negative t over tau factored outside. And this guy is going to, we can rewrite this as vy naught e to the negative t over tau plus vter times 1 minus e to the negative t over tau. So we can examine this equation. If we look at an object dropped from rest, then vy naught is going to be 0. And then we will have vy of t is just going to be, right, this term goes to 0, so that whole term goes away, and then we have v terminal 1 minus e negative t over tau. What this would look like if you graph it on the x-axis, or this horizontal axis, we'd have time, and here we would have the velocity in the y direction. What this is going to do is approach terminal velocity asymptotically, right? So if you remember our objects, if it falls, or dropping it from rest, the instant we drop it, it is going to have some weight force on it. And then the next instant, so this would be like t equals 0. The weight force is going to accelerate it. It's going to speed up, and we know that the drag force is dependent on its velocity. And as it goes faster, the drag force will get bigger, right? So say t equals 1, right? After 1 second, it has sped up to some velocity. So we will have some drag force on it. This is mg. This is F drag. All right. Now, in both cases here, the net force is still not 0, still greater than 0. So it will still have some acceleration. So it will still be speeding up, right? And let's say t equals 2. It becomes very close. This is mg. This is force drag. Right? These two become very, very close. So as time goes on, the drag force, or the object, will speed up. And as the object speeds up, the drag force increases, meaning the acceleration of the object will go down, because the two forces become more and more equal, meaning we get closer and closer to terminal velocity, which is constant speed. That, I think, is a very kind of conceptually not a difficult thing to do. Mathematically, it maybe looks a little weird, right? What is this tau doing? Why is it negative t over tau? Why is there v terminal? Mathematically, it looks a little weird, but I think conceptually understanding what's going on is a very good place to be. But going back to our full equation, because this is still an equation of velocity and we want its position, right? We found the position for the x, now we should be finding the position for the y. And so this will be v terminal naught equals plus vy naught minus v ter, and then the exponential outside, right? This is what we had up above, right? V ter plus vy naught minus v ter. Yep. And we were going to do the same thing, right, as when we solve for position in the x, we're going to solve for position in y. So the position as a function of time is going to be integral, and you start at time equals 0 and go to some arbitrary time t of vy naught dt. Remember, put a prime to differentiate the integral bound and the integrand variable. So this is going to be vy of t. Doing the integral of this, we're going to have v ter of t plus, and then we're going to have vy naught minus v ter here. And then the tau comes down like before when we solve for x. And this is going to be 1 minus e to the negative t over tau. So now that we have the equation for y and the equation for x, because they're uncoupled, because they didn't relate to each other, as I said earlier, which is why the linear term is so much easier than the quadratic term, what we can do is just add these together. And when you do that, the x position and the y position, that is going to get you an equation for the trajectory and the range of an object in a linear medium, which is what I think I will be covering next video. So as far as the math and the conceptual concepts for linear drag, I think that does it. So I will see you in the next video.